So in this video, we're going to talk about two different concepts. The first one is the law of radioactive decay, and the second one is the idea of the half-life. So the reason why we talk about both of these concepts is because if we have a radioactive particle, I'm going to draw a nucleus very poorly here, we know for certain that at some point in the future it will decay. It will give off alpha, beta, or gamma radiation. We just don't know when that's going to happen. And if we have a really large particle that's made up of lots of different nuclei, we know that each of those nuclei is going to decay at a certain point in the future, giving off radiation. We just don't know when that's going to happen. So what ends up happening is this looks like a random chain of events, basically. So at random points in the future, they will give off their radiation. So the law of radioactive decay was come up with to help us describe how we can expect those nuclei to disintegrate, because we don't know when it's going to happen, but we do have some rules about how likely it is to happen and how soon it's likely to happen. So the law of radioactive decay is the first one of those rules, and what it says is that the number of disintegrations per second is proportional to the number of nuclei present. So to put that more simply, if you have a sample of 1 kilogram of a radioactive substance and you have another sample of 2 kilograms of the same substance, well then the 2 kilogram sample is going to have twice as much radiation. We measure that simply by the amount of radioactive particles that come off it per second. So the amount of particles per second coming off the bigger block is going to be twice as much, because the number of nuclei is 2 times as many. If we wanted to express this mathematically, we could do it like this. A is proportional to N, where A is the number of disintegrations per second and N is the number of nuclei present in the sample. So it's proportional because if you double the number of nuclei, the number of disintegrations per second will double as well. Now, like any proportional relationship, we know that we can put this as an equation if we introduce a constant. So let's try doing that now. We can say that A is equal to a constant, which we'll just call lambda, times N. Now lambda is what we call the decay constant, and it'll be different depending on what material we're talking about. So the number of disintegrations per second depends on the material, and it also depends on how many of the nuclei are present. So we have it written out here what each of those different things stands for. A is disintegrations per second, lambda is the decay constant, and N is the number of atomic nuclei in the sample. Now lambda is a constant, so it doesn't have a unit. N is just the number of atomic nuclei, which you can count 1, 2, 3, 4. So again, it does not have a unit. But A, our disintegrations per second, we do need to define a unit for. So that leads us to the becquerel, which has the symbol capital B lowercase q. And a becquerel is the decay of 1 atomic nucleus per second. So if a sample has 2 nuclei decaying per second, then its disintegrations per second will be measured as 2 becquerel. Or 3 disintegrations per second will be 3 becquerel, and so on and so forth. So now we'll move on to the topic of the half-life. The half-life in physics is quite similar to the half-life that we'd encounter in medicine. The half-life in terms of radiation is just the amount of time it takes for half of the nuclei in a sample to decay. So if we have a sample that has 200 nuclei in it, and 0 of them have decayed, and let's say it has a half-life of 3 hours. So after 3 hours, half of those nuclei will have decayed. So there'll be 100 that are left undecayed, and there'll be 100 that are decayed. Now if we were to wait another 3 hours, what we would see is that number of undecayed nuclei would half again. So if we had 100 the last time, I would be down to 50 that would be undecayed. That would mean 150 would have decayed now at this point. And we'll look at one more iteration of this, but we could keep going forever. If we waited another 3 hours, then 25 of these would be left undecayed, because half of those 50 would be decayed now. So 175 would now be decayed. So the reason we call it a half-life then, because the amount of undecayed nuclei halves after each half-life. So after 3 hours it halves, after another 3 hours it halves again, after another 3 hours it halves again. After another 3 hours, what do you think that the amount of undecayed nuclei will be at? Pause the video and press play when you're ready to find out. So after another 3 hours, it will be down to 12.5 undecayed nuclei. Now obviously we can't have 12 and a half that would be undecayed, but this is our best estimate for how many will be undecayed at that point. What this practically means is that 12 would have decayed and the 13th one would be halfway towards decaying. So we'd expect to see it happen pretty soon. So for the sake of mixing things up a bit, we can also look at a lovely warm cup of coffee. I've drawn the cup in black, so then I'm going to have to draw the coffee in red. But a cup of coffee, if you make it yourself, has about 80 milligrams of caffeine in it. Now, some people might make it stronger, but that's maybe a good ballpark estimate for a home brewed cup of coffee. Caffeine is a half-life of about 5 hours for most people, although it does vary. So the symbol we're going to use is T 1/2. T normally stands for period of time, or a length of time that repeats itself. So the half-life is, we'll say, about 5 hours. So if you take a cup of coffee in the morning at, let's say, 11 a.m., then you're going to have 80 milligrams of caffeine in your system at 8 a.m. Now that should half about 5 hours later. So 5 hours later would be 4 p.m. So at that point then you'd have 40 milligrams or half a cup of coffee left in your system. If we wait another 5 hours after that, we'll be at 21:00 or 9 p.m. So at 9 p.m. you've still got 20 milligrams of caffeine in your system, which is about a quarter of a cup of coffee. So we can see how this would cause problems then if people started having caffeine later on in the day, like 2, 3, 4 p.m. And then they'd have really substantial amounts left in their body when they're trying to get to bed. And what's really important just to take away from this screen is T 1/2 is the symbol that we're going to use for half-life. Now the final thing to be covered in this topic is just the relationship between the half-life and the decay constant. So the decay constant we already mentioned will vary depending on the material, and it also makes sense that the half-life would vary depending on the material we're talking about too. So the two of them are linked by this formula. It might look complicated because we have a natural log here, but it's the half-life is equal to the natural log of 2 divided by the decay constant. This actually is pretty simple to do, even though it looks maybe a little bit intimidating, because the natural log of 2, you just put it into your calculator and it gives you a constant. It'll be the same every time. And in fact, I'll tell you what it is now. It is 0.693 recurring. So it'll just be that same number. I generally take it as 3 decimal places, unless they give you a very specific amount of decimal places in the question. Like if they use 5 decimal places as the decay constant, then I would use 5 for anything else I'm putting into that calculation.